It's not much of a serious at all, because when you're trying to connect things in a straight line, when you're trying to connect at least two outer atoms to a central atom, the best way to do it is through a straight line or 180 degrees. But let's discuss that a little bit further. Okay, so let's look at CO2 Lewis structure. We have a central atom, right? And it's got two outer things connected to it. And so when you count the electron sets around the central atom, you have one here and one here. Remember, the double bond counts for one. Okay, so two electron sets. So the electron pair geometry is gonna be linear, right? Now, when you're looking at the molecular geometry, it's gonna be the same because you got no lone pairs on the central atom. So two bond pairs, zero lone pairs, right? And so the molecular geometry is also going to be linear. And as you heard me mention already, now if you have something in the middle and two things surrounding it, the bond angle here is going to be 180 degrees. Now, what is is this polar or non-polar? So you've got to ask yourself, do I have polar bonds? And when I'm talking about that, I'm talking about the individual bonds. So CO, is that a polar bond? It sure is, because oxygen is rather electronegative. It's right next to fluorine. So it's more electronegative than carbon, meaning it's meaner than it, stronger than it. So it's going to be pulling the electron density this way, right? Making this partially negative and this partially positive. But what do you have on the other side? You have another oxygen who's pulling on an equal and opposite direction, okay? So what do you know about this? The molecule overall, this entire molecule, is it polar or non-polar? So even if you have polar bonds, but these two are exactly the same, it means they're tugging in equal opposite directions, so the molecule overall is non-polar, okay? I don't care if you have, like I said, hooks tugging in on these electrons. They're pulling in equal and opposite directions. So this is pulling right, this is pulling left, they cancel out, okay? So that's why this is non-polar. Now, let's look at this one here. Central atom here, carbon. How many electron sets are around here, guys? Triple bond counts for one. So 1 and 2. 2 electron sets. So the electron pair geometry is linear. Now, how many bond pairs and how many lone pairs, right? So this is bonded to two things. So 2 bond pairs. Now, 0 lone pairs. So of course, your molecular geometry is also going to be linear. Your bond angle is also going to be 180 degrees. Now, when you do that on a model, right? So what are we going to do here? We're just going to get rid of one of these, like so, and then we're going to make it a triple bond on the other side. Okay? Okay, so here's how that looks, right? Here's my triple bond right here, and this is my single bond, like that. Okay, now it's still linear, is it not? But is this molecule polar or not? Here's your central atom. Now let me put something here so you can see it. Let me change this one. Okay, now look at this. What should be the first questions you should ask yourself, right? We do have polar bonds. The CN is a polar bond, right? But what you need to really look at to help you figure this out quick is that, do I have two of the same things on the opposite directions here? They're different, right? So they're different, meaning one is stronger than the other. So here in this case, the nitrogen is more electron negative than the hydrogen, right? So the electron density is going to be pushing this way towards the nitrogen, right? Leaving this partially positive. So the electron cloud is going to be more right here, okay? So yes, this is polar because there's two different things on the central atom. Got it? So this would be polar molecule. Yes. That sums it up for the linear series, which is not much, right?